Hi everyone, my name is Daria Hasanova,
And I'm Anna Johnson.
and today we're presenting on rotational kinematics and torques, but we're relating it to pregnancy and back strain. So, why do pregnant individuals experience back pain? Well, it turns out that during pregnancy, the center of mass is actually shifted drastically forward, and this is because a large mass is added to the front of the body. And so what happens when the center of gravity is shifted, right? So when it's shifted, the pregnant individual is placed into what is called an anterior pelvic tilt. And this is basically a position in which the stomach bulges forward and the pelvic muscles get overstretched. And what this does is this causes the upper body to sit over the pelvis rather than on top of the pelvis. And this causes the spine to curve. And on average, an individual gains roughly 30 or more pounds by the time they're ready to give birth. And this accounts for things such as the size of the fetus, the placenta, the amniotic fluid, breast size, and more. And when this increased mass of the belly pulls on the spinal cord, it also contributes to that increased curvature of the spine, which in turn places more strain on the back. And we can see the images on the right where the spine becomes more curved over time as more strain is put on it by the belly. So, how does this topic relate to torque? Well, when any object rotates in space, it exhibits two types of motion, normal projectile motion and rotational motion. These can be described as the motion of the center of mass, which includes things we covered earlier in class, like kinematics, dynamics, and the conservation of energy laws, or the motion around the center of mass, which are rotational kinematics, rotational dynamics, and rotational conservation laws. And this motion can be explained by two concepts. This would be the moment of inertia and torque. The moment of inertia serves as the rotational analog of mass, and it tells us how hard it is to rotate an object around a given mass. So the heavier the object is, the larger moment of inertia it would have because it would be harder to rotate. On the other hand, torque is the force applied to cause an object to rotate around its pivot point. And we can see below that torque is given by the following equation, where it is either the moment of inertia times the angular acceleration, or it's the distance from the pivot point to the force applied times the force applied times sine of theta. And we see here that torque is directly proportional to the moment of inertia. So if one were to increase, the other would increase proportionally, unless, of course, there was a change to the angular acceleration. So how does torque apply to pregnancy? Well, looking back at the formula that is shown above, and it tells us how to calculate torque, we can see two things. The first thing is that the torque equation incorporates force. And if we think about it, the force would be increased due to the heavy abdominal weight caused by the pregnancy. And then we also have R, which is the distance from pivot point to force applied. And if we also think about this, the R value would also be increased due to the increase in size of the abdomen, which increases the spine's distance to the abdominal force pulling down. And in this case, the spine is the pivot point because that is the location in which like the bend occurs. Since both the distance to the pivot point from the force and the force itself are increased in a pregnant individual, we would naturally expect that the back muscles need to exert an equal torque on the abdomen to counteract the force that is being made by the belly. And this would assure that the woman does not fall. So an increased force exerted by the back then would also cause increased strain on the back and discomfort in the pregnant individual.
All right, so now that we have all this background information, let's walk through an example problem and apply what we know about torque. Our example today is considering Susan, a pregnant woman, picking up a large Amazon package that was delivered to her front door. And we assume that the mass of her upper body is 45 kilograms, the mass of her pregnant belly is 12 kilograms, and that the mass of the Amazon package is 16 kilograms. We are to determine the force, magnitude, and its direction exerted by the back muscles to counteract the rotational torque of the belly. And secondly, we will be finding the force that her vertebrae exert on the spine at the pivot point. So we drew a little diagram and we applied model, visualize, solve, and review. As you can see here, we have Susan who is picking up her Amazon package. We are modeling rotational dynamics, kinematics, torque, and lever arms in this. Our visualized component of our problem, we drew free body diagrams on the actual diagram. Our pivot point is actually right here in pink, and our vertebrae is right here of her spine. Our mass of the box located right here with a downwards force for the weight of the box. We also drew the upper body center of mass as well, which we indicated right here. And we also included the pregnant belly, which is indicated right here. Now I will explain the R values that we determined and how we determined it. First R value, we did the perpendicular distance from the pivot point to the upper body center of gravity. Next, we did the R value for the belly, which is the distance from the pivot point right here to the pregnancy weight. And then we did the R value for the box, which is also the distance from the pivot point to the box's center of gravity. And then lastly, we have a small perpendicular lever arm right here, which is distance from the pivot point to where the back muscles exert force. So we can see here we have our force of the back muscles and the force of the vertebrae. Force of the back muscles are counteracting the forces. So here we indicated that all of these three forces will be in the clockwise direction, and then the back muscles will be in the counterclockwise direction. This 30 degrees indicated right here is the angle between the back muscles and the spine. The 60 degrees indicated here is the angle between the spine and the horizontal direction, and it indicates how far the upper body is bent forward during the lift. The 40 degrees indicated here is the angle between the line connecting the pivot point to the center of gravity of the upper body and the horizontal. This angle helps us calculate the torque created by the weight of the upper body. And then lastly, the 20 degrees indicated here is the angle of the vertebrae force direction relative to the horizontal. I also want to indicate here the 6 centimeters. This is a smaller lever arm because the vertebrae is pushed back due to the enlarged uterus, which indicates the large curvature of the spine, as Daria mentioned earlier. All right, so in part A or part one, we are going to figure out the force of the back muscles, and we are going to be comparing that to the total weight. So firstly, we started by calculating the weights of the upper body, the weight due to pregnancy, and the box. So by doing that, we're given all our mass values and multiplied all of those by the force of gravity. Then we used torque equilibrium equation. The torque equilibrium equation we used was R perpendicular times force. We added up the three forces that are going in the clockwise direction and equaling it to the counterclockwise direction as the force of the back muscles are counteracting this opposite rotation. We found our torques summed in the clockwise direction. We solved for the force of the back muscles. So we yielded a number of 4,753 newtons. And then we compared this to the total weight. We divided the force of the back muscle over the weight total to yield 6.64, which is approximately 7 times than the weight being supported. This demonstrates that there's a significant strain being placed on the spine. And then in part B or part two, we are finding the force that her vertebrae exert on the spine at the pivot point. So we started with finding the vertical force component of the vertebrae. We applied Newton's second law here, where we subtracted all of these and the net force was 0, but we rearranged it to look like this. So the vertical force of the vertebrae is equaling to the sum of all the forces, and we yielded 3,091.9 newtons. Similarly, we found the horizontal force component of the vertebrae, and we yielded 4,116.1 newtons. We found the magnitude of the force of the vertebrae via the Pythagorean theorem, and we got a force of the vertebrae of 5,148 newtons. To find the direction of the vertebrae force, we did the inverse tangent, and we divided the vertical force over the horizontal force, and we got 36.91 degrees. A little check or review for this is as we increase torque in the clockwise direction, the torque exerted by the back muscles must also increase to counteract it. So future directions, how is the back strain relieved for pregnant individuals? And is there any technology that exists to do so? We found that the effect of kinesiotaping actually relieves some low back pain during pregnancy. As you can see here, this is a common place to put the tape. It could also be placed on the lower back as well. Studies have shown that kinesiotaping could significantly improve back pain and strain. The tapes can redistribute the weight of the pregnant belly so that the center of gravity is not shifted so far forward. The tapes actually also stabilize the spine and bring it in alignment with the upper body, and this reduces the strain put on the back muscles as well.
And then we just have our bibliography at the end. Thank
Thank
you.
you.